Not a problem at all.
Okay, so this is Professor Arnab Roy from Indian Institute of Technology, Kharagpur. So he is our the keynote speaker, and his talk will be brief review of wave energy using oscillating water column. So Professor Arnab, you can just introduce yourself and you can start your presentation.
Sure.
Thank you.
Thank you. Thank you very much, Professor Rasool. So let me share my screen. Can I go ahead?
Yes, please go ahead.
Thank you. So are you all able to see my screen?
Yes, we can see.
Okay, great. Thank you. So thank you very much, Professor Haroon, for allowing me to start my keynote lecture. So I come from the Indian Institute of Technology, Kharagpur, which is located in the eastern part of India. And this happens to be the first Indian Institute of Technology established way back in 1951 in India. And with this institute, many more Indian institutes of technology came up in later times. We have more than 20 such institutes now in India spread across the country. So this is one of the oldest IITs, in fact, the oldest, and we have about a 2,100 acre land over which a large number of departments and centers and schools are spread. We have more than 12,000 students on campus, more than 800 faculty members. And I'm very proud to be a part of this institute, and I'm presenting this work on behalf of the institute. So I work in the Department of Aerospace Engineering at IIT Kharagpur as a professor. So I'll just start on the lecture topic. We are looking at a brief review of wave energy using oscillating water column. So let's look at the content. So as you can see that wave energy, it is very essential for us to be tapped in, especially in countries which enjoy an extensive coastline, and we have to go greener, and we have to exploit the potential of this energy more and more in the times to come. The very challenging part of wave energy is how to extract it with efficiency, good efficiency. And one of the ways by which it is done is to place an oscillatory water column device into the sea waves in the form of a duct, and then try to capture the oscillating water waves within the duct, and the air above that keeps on moving up and down with the waves, and that is fed into a suitable air turbine which can extract the pneumatic energy available in the oscillatory flow. But since most of our turbine designs are based on unidirectional flow and they are optimized that way, it's very difficult to use such designs ad hoc into this kind of a challenging situation. And therefore, there are issues related to the design which needs to be looked at carefully. So we are seeing a typical oscillating water column plant, a kind of a sketch of that, in which you can clearly see that there is the ocean water coming into the base of that oscillatory water column duct, which is in the form of a concrete caisson. And because of the movement of the oscillating water column here inside the duct, the air above it also keeps oscillating. And that's fed into this duct. And there is a suitable air turbine placed here, which is often called as a self-rectifying turbine, which can handle the oscillating air. And a self-rectifying air turbine capable of rotating in one direction under the bidirectional flow conditions and not requiring a rectifying valve system is what is required for effective operation. And it can be employed to convert the low pressure pneumatic power to mechanical energy. So typical flow rates that you may be looking at here is of the order of 10 to the power of 2. And typical response times are typically, they are less than 1 second. So the turbine has to quickly respond to the changes in flow direction and without hampering its efficiency significantly. Till date, mostly 2 different axial flow machine designs have been used. One is the Wells turbine, the other is the impulse turbine design, but of course adapted suitably to these operations under oscillatory flow conditions. Wells turbine, of course, has been designed that way that it can effectively operate in oscillatory flow. But impulse turbines, as we know from our experience, we might have learned them as single-stage steam turbines in de Laval's design. But here, in the oscillatory flow situation, the rotor is accompanied not by a single row of guide vanes, but rather 2 rows of guide vanes, which are placed on either side of the rotor, so that they can handle the incoming flow irrespective of the direction and orient themselves in a suitable way so that the rotor gets a flow which is effective for its operation. And several versions of these turbines have been developed over time to address the efficiency issues and other environmental issues related to a lot of sound generation. There are still major challenges to make them more effective. Let's have a brief look at the scheme of the Wells turbine. So you can see a picture here, a rough sketch. So I've used a lot of rough sketches, more like the ones we use on our blackboards, or when we try to draw simple diagrams using a pen and paper. So here what you see is that there are symmetrical airfoil blades in the sense that they have a symmetric thickness distribution about their cord line, which are mounted on the hub of the turbine. And the turbine, of course, is connected with an electrical generator. And it's within this duct, which is shown in dotted lines. And of course, this duct is placed into the ocean so that the oscillating water column can be housed inside. And a lot of work has gone on in trying to refine the design, in trying to choose different geometric sections for the airfoil, which makes it more and more effective. The basic principle is that when there is an axial flow coming in from either this direction or from top, depending on the phase of the oscillating water wave surface, the symmetric airfoil section tries to generate a force which is basically due to a combination of velocity components. So it has a peripheral velocity, which is marked with U, and then this is the axial velocity component. And then with a vectorial addition, you get the relative velocity. And the condition is that irrespective of the flow direction, an effective force is created which has a component in the tangential direction and which is consistent irrespective of the flow direction. So that's the principle of Wells turbine. But the unfortunate part is that when the axial velocities become large, the blade stalls, and therefore it becomes aerodynamically ineffective to generate this torque. A lot of airfoil sections have been tried, but one of the most successful ones has been the NACA 0015 blade. When you increase the solidity of the cascade, that means you put in more blades and you have more number of blades filling up that annular area, usually the performance increases. You could also try different duct designs or blade tips, shapes in order to reduce tip stall, or you can use variable pitch and variable chord along the blade span to improve its efficiency. A lot of these have been tried in permutations and combinations with limited success. Of late, a passive flow control method has delayed stall quite significantly and says that it would improve the blade torque coefficient maybe up to 40%. But this needs to be proved through field trials. So this is a brief on Wells turbine. Another turbine that I was talking about, that is the self-rectifying impulse turbine design, that looks more like this. So you have a rotor row comprising of impulse blading, and then you have a pair of rows of inlet and outlet guide vanes. And mind it that you have them functioning in oscillatory airflow, and therefore, if at some point of time the flow is coming in from right towards the left, then this row is functioning as inlet guide vanes, while the other is functioning as outlet guide vanes. And when the flow reverses direction, it's moving from left to right, then this row is functioning as inlet guide vanes and the other as outlet guide vanes. And when they function as inlet guide vanes, they are closer to a nozzle configuration. And when they function as outlet guide vanes, they are closer to a diffuser configuration, which makes the pressure recovery more efficient. So this is something that I have taken from a report and part of my work, which I had done a couple of years back as a part of a project in another Indian Institute of Technology as a part of my master's program also at IIT Madras. So we'll look at what project it was all about. So here we are trying to look at some of those old drawings where we used to do it, on a drafting board. And here you can see some parts of self-rectifying air turbine, which we had built in a laboratory at IIT Madras to see for ourselves how these turbines function and try to quantify its performance. So here you can see that you have the rotor shaft carrying a large number of blades, and which are mounted on the rotor hub. There are about 50 odd blades, and the blades are located here. And on the two sides are the two rows of guide vanes. And interestingly, they are also connected using a 4-bar linkage. And those guide vanes can be pitching between two limits of angles, which can be altered if you wish. And then in order to ensure smooth flow through the air turbine, we had a belt mouth design. We had certain features which we had incorporated into the design on our own, and some of it was motivated from a design which we got from Professor Sitoguchi's group in Japan. So just to look into some details, so these are some of the details of the rotor geometry and guide vane geometry in terms of the blading. And the rotor had about 30 blades in this design. We made another where there were more blades, about 50, and 26 guide vanes on two sides of the rotor. And the rotor blade profile is elliptic shaped on the suction side and circular arc shaped on the pressure side. And the camber line of the guide vanes consists of a straight line and a circular arc. And additionally, you can see that depending on the flow direction, they take different orientations. There could be two different designs here. You could keep the guide vanes self-pitched in the sense that depending on the airflow, the conditions of the, the turbulence, the magnitude of the velocity, etc., you can leave the guide vanes free to pitch on their own. So that is a self-pitch controlled guide vane mechanism, while you could also connect them with a 4-bar linkage like I was describing, and we pursued this design. And then we had an oscillatory flow test rig to perform this study. Of course, that would ensure that you would have a sinusoidal flow into the turbine. And what it was doing was basically there was a moving piston inside a duct, and this piston was reciprocating back and forth. That was creating an oscillatory airflow through the ducting which contained the air turbine. And as you can see that this was part of a project sponsored by National Institute of Ocean Technology, NIOT, at IIT Madras under the Department of ocean development, Government of India. So that was the time when along the western coast of India at several locations, wave energy plants were being developed. And this study was part of the prototype development. And we had a small test setup instrumentation as well to quantify the performance of the system. So the input power, you have to measure the pressure drop, you have to measure the flow rates, and then on the output power side, you have to extract the information about the torque generation, the angular velocity at which the turbine is rotating, so that you can quantify the performance of the turbine. And you also have to assess the losses. For an example, I'm just showing some kind of snapshots of that report, and you can see that typically if you look at the pressure drop across the turbine during an oscillation cycle, it has close to a sinusoidal pattern. Of course, it will not exactly match with the kinematics because, as you know, fluid dynamics has its non-linearities, and with the differences in the flow velocities, etc., there would be some changes. Also, the input mechanical power versus alternator output current was worked out at different RPMs. And then we were looking at how effectively the guide vanes were pitching between the two extreme angles. So these were the two angle settings, the upper and the lower side. So at one point it was functioning as a nozzle, another point it was functioning as a diffuser effectively as the flow was changing direction. And finally, when you try to quantify the performance, you look at how your input power coefficient went as a function of the peak flow coefficient phi. So this is how the input power coefficient varied. Nearly, you could say close to linear behavior, but there's a bit of non-linearity. If you look at the best fit plot, the torque coefficient was closer to linear. And when we tried to, based on these metrics, when we tried to plot the mean efficiency, because you have to average it over the cycle, the mean efficiency as a function of the peak flow coefficient came out like this, where you can see there were some differences with the Japanese design from which we got the motivation, but we did some changes in our design too. And what we found was that our peak efficiencies were shifting to higher peak flow coefficients. And there was a marginal improvement on the peak efficiency side. But then based on the limitations in the time, we could not extend our measurements to beyond this range of phis, and that would be interesting to do and see how this model would function. But it broadly correlates with what the Japanese design was. So we would be sure that the performance looks more or less like this for impulse turbines with self-pitch control guide vanes. And this performance is superior to the one where you have them as the ones which are connected. Here is an interesting review of one paper where you'll find a lot of activities going on in the CFD world, where these days we have more emphasis on simulating flows through such reciprocating flow air turbines. So this is a recent paper where they have tried doing finite volume solutions of the Reynolds average Navier-Stokes equations in their unsteady form. Remember that you have to simulate it as an unsteady flow and complex geometries, moving boundaries. So there are a lot of challenges involved in these computations. And the idea is that these type of numerical simulations will help drive the design improvements of air turbines in future, but they have to be very carefully validated with experimental data. So a couple of years back when we performed our experiments, the CFD tools were still not there, still not so well developed. We never thought of doing such simulations to check whether the simulations can really do well with experiments. But I think the time has now come where we can do these exercises increasingly so that We can validate the numerical models also significantly and gain confidence. And thereby the design optimizations can be driven strongly by simulations and carefully validated with experiments. So let's look at a few challenges. So when we are talking about actual operations of these air turbines in OWC devices at site, so they are basically functioning under adverse conditions. So there could be extremely high speed waves, high amplitude waves, which could lead to catastrophic failure, typically mechanical failures. And then there is the corrosive nature of the ocean environment, which could be very detrimental for the turbines. So improved materials could be one direction in which the research should look at. Then we need to minimize OWC and turbine aerodynamic noise, because very often they are close to the coast, and many of such coasts, especially in populated countries like India, are thickly populated, and therefore there are environmental issues. So studying the aeroacoustics of OWC and turbine assembly to reduce the sound pressure levels, that is the unsteady sound, pressure field which is generated by such devices, by maintaining smoother, unseparated and unstalled flows over the surfaces, over the blades, is very, very essential. And usually low rotor speeds would reduce the noise. Additionally, you could have noise attenuation chambers, but the issues are that they could be counterproductive as far as the turbine performance is concerned. So we have to do that with care. Usually the impulse turbine design is superior to the Wells turbine design in terms of noise. One reason being that it functions at a lower speed. But that's not all. There could be promise even in the Wells turbine design, or could be newer designs, which we are yet to see. Assessing turbine performance in the environment of random waves remains a challenge, because there are differences happening over the day with rising and ebbing tides, and there could be climatic changes, very rough weather, under which environment plays a big role, and turbine performance assessment under such conditions over a long period of time is a challenge. And these are very difficult to test in experimental facilities, because there are large uncertainties in nature which we cannot really replicate. Even in CFD simulations, if you are using a Gaussian distribution for the wave surface displacement or the unsteady pressure in the OWC, they are not very easy to implement in the models. Additionally, till date, whatever simulations are going on are from the URANS side, but since these are very unsteady flow fields, you need to look at things like detached eddy simulation or large eddy simulation, which are more recommendable. And therefore, design optimization in such a random environment is a big, big challenge. Now, minimum variations in the mean power output is also not very easy to reach because of the highs and the lows in the tides across the day. Therefore, sometimes it happens that it is drawing from the grid instead of delivering. Effective use of passive and active flow control strategies in random wave environment is felt to be one of the solutions. Experts do agree on it, but they are not very easy to impose. Especially active flow control could be quite tricky. So we conclude by saying that there are still several challenges which exist today in enhancing efficiency and effectiveness of energy extraction from OWC-based air turbines. Though many of the studies have been based on conventional turbines, but their design had to be extended to fit into this framework, and they do not function all that effectively in oscillatory flow. The turbine and duct assembly design has to be optimized with regard to various aspects like maintainability, noise reduction, robustness of the design, superior performance under random wave conditions. So there are multiple objectives to be met at the same time, which is usually the case. It's a little more challenging here because of the uncertainty of the flow field. Adaptive design features and flow control has to be implemented into the turbine and OWC system for more optimum performance. So with this, I come to the end of my lecture. Thank you for patient hearing. So if there are any questions, I'd be glad to take them.
Thank you, Professor Arnav. It was a really, really good presentation.
Thank you,
I
Professor
know your
Rasool.
thank you. I know your topic, or maybe your presentation was quite intensive in terms of the technical information. But from layman's point of view, there could be many people, not maybe from the wave energy area. So they might have said different or simple type of question. So I'm asking question from the floor. Do you have any question from anybody? So presentation was, I think, about 24 minutes. So there should be some question, isn't it?
Can I kick it off?
Yes, please. Yes.
Well, yeah. I think just a question that link this type of turbine to wind turbine in a way, because wind turbine you have cut in and cut out wind speed. So I believe that this type of turbine you may have like wave high cut in and cut out speed or something like that. Can you
Yeah, I mean, yeah, it's a very pertinent question, but it's difficult to really set those borders, because once you try to limit them, you need additional mechanisms perhaps in order to do that. And then not that those techniques haven't been tried till date, but the overall system performance does get compromised. So beyond a point, they have left it open to nature to provide it with the uncertainties and manage. So that's the state of affairs at this point, but I'm not very sure whether there's a very latest development which is under the sky, which I am not aware of.
No.
Thank you.
Thank you. Professor Arnav,
Yes.
like you got oscillatory turbine compared to our maybe versus to the normal turbine. When you put it in, say, ocean is coming, the flow is coming, and putting turbine, and you're producing power. So how do you like convince people that, okay, your system definitely is better than the normal or the traditional one? You might say that in terms of efficiency, but in terms of complicacy also. So do you want to just give a bit of information to the audience?
Surely, Professor Rasool. So, of course, there are different options of tapping tidal energy. We are well aware of that. And this is just one of those options. I would put it this way, that if you have a reasonably simple, cheap design, which doesn't need to be maintained very often, and we can have a humble target of having a small town powered by the energy of a number of units which you deploy along your coastline, which doesn't need much maintenance. You know, you have to just go back to that turbine and find out whether everything is fine, maybe in a couple of weeks' time. You don't need to intervene in between. Then people won't mind to make that investment, whether it's from a government level or from a local body.
Yes.
So that's where I think the efforts should begin at this point. I mean, I don't think we could draw very major investments right in the beginning. That's how it has happened in India too. That very small projects have started. Only small localities have been powered with medium scale investments. The main issue has been that if you need to maintain it infrequently, you don't have much of trouble maintaining it, because the turbine has a rather robust and kind of simple design. I think that is where we can encourage people to get into this mode.
Okay, no, thank you. I think it was.
Can I have a quick question, please?
Very
Yeah,
quick,
please,
because the time is almost 1:30 and we have to start with that.
Professor Russell, can I have a quick question, please?
Yes,
Sure.
yes. Just,
Professor Roy, can you give us some idea about the material used to build and the cost, investment cost involved when you mentioned that it might be suitable for India, it might be suitable for Thailand too.
Yes, yeah. Thank you very much, Professor Nakron, for the relevant question, because I was talking about rather inexpensive units. So as far as I know, when I was participating in that project, a lot of this construction was planned using FRP, fiber reinforced plastics, and ones which do not need to be finished to a very, very fine surface finish level, because a minor, tolerance level alteration at the blade surface, etc., should not make the performance degraded significantly, because anyway it's going to be in a very uncertain environment. So that was the emphasis, and what came out of that was that in terms of Indian costs, I do not exactly know what will be the conversion in terms of your currency. So in Indian cost, typically each unit, which would be about, say, a meter in diameter, which is a very small unit typically, would cost you about 4 to 5 lakhs when it is mass produced, which is not a very big cost really to begin with. Maybe
in US dollar, please.
In US dollar, typically it would be, say, about 6,000 US dollars, 6 to 7,000.
Yeah, I think Professor Nakon, maybe if you have some more question, you can talk to Professor Arnab separately. And we are already over time in the first presentation. So we need to quickly move to the second presentation. And the second presentation is on paper number 20. And the presenter is Dr. Karakot Tipayong. So are you ready, Dr. Karakot?
Thank you very much, Professor. Today, I will ask my research assistant, my student, to present this paper instead of me, but I'm still here. So I would like her to work on.
No problem. Ask her to just share the screen first.
Okay,
and
thank
then
you.
Maybe ask her. Okay, can you also introduce yourself, presenter?
Okay.
Just maybe 30 seconds, maybe.
Yep, the presenter today will be Ms. Jidapha Chanjaran, my student, my postgraduate student. So she involved in this work, and she would like to give you a presentation on the topic of the. Can you share the screen now? The potential use of various biomass sources for operating cost reduction in a power plant in southern Thailand. So, Jidapha, please.
Yeah, can you just do the slideshow, please, so that we can see the whole screen, your PowerPoint? Otherwise, there are a lot of other things. The slideshow. Okay, yeah, that's good. Please go ahead. Okay. So, is there any problem?
I think she's still muted.
We cannot hear anything. Okay. So, Dr. Karakot, are you having any problem? Or maybe your student having problem?
My name is Jidapha Chanjaran, Faculty of Engineering, Chiang Mai University in Thailand. Today I'm going to present about the extension of my research in the title of potential use of various biomass sources for operating cost reduction in a power plant in southern Thailand. So the contents of the presentation are going to start with introduction, problem statement, and objective. Then we collect all data to clustering them and determine centroid of each cluster. Biomass production costs was also collected and used them when we develop the optimization cost model. And then we talk about results, case study, and sensitivity analysis. And the last one is conclusion. Agriculture is extremely important in Thailand, as you see in pie chart. 34% of the population is engaged in sector, and it represents the largest career proportion. It causes a lot of agricultural residual every year. This slide shows the top 10 out of 23 kinds biomass. They were accounted for 90% for all sources in Thailand that we focus in our research. The most volume is gas, and second is rice straw, third is fronds, sugarcane leaves, maize leaf, and stalks. The sixth is cassava peels, husk, cassava rhizome, empty palm bunch, and the number 10 is rubber wood chips. Transforming them to renewable energy can benefit the country rather than burning them. In southern Thailand is rich with many biomass resources. Entrepreneurs from this part of the country also enjoy special privileges from the Royal Thai government in establishing business and employment, especially those in a three border. Most power plants utilize a single source of biomass residue, which usually is rubber wood waste. Cost is a crucial factor affecting the business operation and long-term success in the use of biomass energy projects. Although Thai government support and promotes the use of green energy, that industrialists and entrepreneurs have a huge opportunity and potential for electricity production from biomass. But the results still unsatisfied because they're not confident to get involved in their policies. So a study on cost optimization for power plant is needed. Cost is a major factor that affects the competitiveness and long-term success in the use of biomass energy. Therefore, we develop a cost optimization model to provide minimum biomass and transportation costs for specific users. Furthermore, the model can be used as a tool to evaluate intermediate biomass materials and their sources before actual production. Hence, in this study, a previously developed cost optimization model was adopted and applied to a case study of Yala power plant in southern Thailand, where reduction in biomass and transportation costs for electricity generation was demonstrated. Two types of data of over country were collected. First is a demand of biomass and world core destinations. In Thailand, 230 power plants locations were gathered into 160 sub-districts. Another one is supply and biomass available locations, top 10 agriculture residuals claim come 6 different types of biomass plants: sugar cane, rice, biopalm, maize, cassava, and rubber wood. All supply data were gathered into districts. A number of districts depend on plants. The biomass potential of each type to produce electricity was also corrected to evaluate number of use and cost. As you see in the table, sugarcane is including bagasse and sugarcane leaves and shoots. Stalk and husks are from rice. Oil palm have frond and empty palm bunch. Maize has only leaves and stalks as well as rubber wood. And last one is cassava that include peels and rhizomes.
Yeah, can you please go a bit faster because
We
time
use
is
data
almost finished.
clustering and centroid determination because demand and supply have a large amount of data. Coordinates of each biomass demand and supply size in one demand type, and 6 supply types of plants were grouped via k-means clustering method, as you see in the left picture. And right picture is the result of power plants clustering from latitude and longitude. C stands for cluster.
Can you please go to the
So
results because you
the
don't have
power
that much
plants
time
have
left.
3 clusters. That the optimal number of clusters was defined by the highest silhouette score. After clustering data, we determine a centroid coordinate of each cluster to be representative. In demand cluster, we calculated a centroid from the number of power plants and energy requirement. Meanwhile, a supply centroid was determined based on the quantity of biomass only. Cost of
Dr.
production
Karokat,
was
we have
divided
to
into
go quickly.
Okay, she will try to conclude it now.
Yeah, thank you.
Howdy.
Okay, so looks like the share screen is okay.
a case study of Yala biomass power plant situated in southern Thailand was considered. At present, the power plant generates 7.5 megawatt electricity from using residuals solely as fuel. For this case study, the Yala biomass power plant is part of rubber wood chips. There were 3 potential agricultural residuals that was available within a 120 kilometers radius.
Maybe just summarize the Dr. Karokat. Maybe I don't know whether she can hear me or not. Just summarize.
Okay, I will summarize it here.
Yep.
The results show that total biomass supply to electricity production cost was about 87.03 million baht per year, with biomass cost of 61.06 million per year, and the transportation cost of 25.97 million baht per year. by using rubber wood chips, rice residual, and oil palm empty fruit bunches from 1933 and 35 sources. In comparison to the original situation, 100% rubber wood chips, the proposed operation used 3 types of biomass. It was found from the cost model that changes in the biomass supply can reduce the total cost by 37.8 or about 52.89 million baht or around 1.7 million US per year.
Okay. Now I think
And
that's
discussion. In this
So
case study, the most variable.
Can I ask you to stop because time is over now?
Okay, sorry, Professor. In this work, we try to do the simulation that if the power plant, they switch the source of energy from existing to another source, so it will cost them like less cost in terms of the transportation and the material cost. So we generate this kind of database for the power plant industry. Thank you very much.
Thank you. I think it's a nice saving, about 38% cost reduction, which is quite good. But unfortunately, we have only maybe time for one question because we have to go to the next presenter. Is there any question from anybody? I will just take one question, not more. Okay, looks like there is no question. So thank you very much. And I think definitely it was a very informative presentation. And we'll see if someone are interested to do this research or this type of research, you can contact the author separately through email.
Okay, thank you very much.
Thank you very much.
Give me question later on. Thank you.
Okay, thank you. Our next presentation is number 45, but that is on the video presentation. So what I'll do is I'll just run the video and it will continue for 9 minutes and 14 seconds.
Good morning, my name is Shaila Sagawi.
Just 1 second here. And then is the presenter around or attending for paper 45?
Yes.
Okay. Just I'll run the video first and then we'll ask for question. Okay, so I'll share the screen. Then this one, then share. And
Now I am studying is master degree of engineering program in renewable energy engineering at Metro University. The topic of the presentation today is a review of thermal efficiency and optimal design and biomass gasifier stove. Dr. Pakamon Pintana is my advisor. The main of topic presentation are introduction, the study result from gasification and the design to biomass gasifier stove and the performance of them. Biomass is the first highest resource of primary energy globally, following oil, coal, and gas. According around 1/3 of population in development countries lacks availability of clean cooking facility, incomplete solid fuel combustion in biomass cook stove release a great amount of hazardous smoke, which contributing of significant health risks. There are several research of design biomass cook stove. It depends on their focus on type of gasifier air supply control and biomass gasifier is system to development the efficiency of gasifier stove. Moreover, there are a few review overall design biomass gasifier stove. In general, the biomass combustion is inadequate for the thermal energy to sterilize. Combustion efficiency is low with high smoke emission and process control is limited. This review article focus on design biomass gasifier stove for maximum thermal efficiency. The main characteristic of biomass that have an effect on the design of the gasifier design and operation are also included in this work. Let's start with this content biomass gasifier. Biomass gasification. Gasification process contain of 10 reaction. Combustion and heat transfer. Combustion define the process by which air and fuel react chemical at sustained higher temperature. The gasification process, which includes drying, pyrolysis, oxidation, and gasification, and heat transfer is commonly known to be the process by which transfer of heat generated from combustion occur on a heat absorbing surface. Let's move on the next point. Biomass gasification stove design from study research therefore the information was divided to 4 content such as material, main design, air supply, and system. Material, there are many types of material are used to make a small gasifier, such as clay, ceramic, and metal. With more than one material used for different components. The material classification is useful in designing based on locally available raw material and the proper production process. The simple stove is made of clay. Nowadays, many improved biomass stoves are made of metal, which insulator despite the highest cost. Cylindrical biomass furnaces were fabricated using locally, and the typical type of biomass gasifier includes hot dap, down dap, and up dap. And these materials have a wide range of thermal conductivity, indicating their different thermal conductivity. As a part, the characteristic of most biomass stove is natural dap. Is it easy and economical to produce? It depends on the winding force type in the movement of the fluids by which convection heat transfer takes place by 2 different mechanisms. On feed system, the biomass stove have different parts of the biomass feeding inlet between the primary air inlet and secondary air inlet, or is on the top of the top list of the gasifier. Biomass has significantly higher bulk density than dry fuel because biomass with high density with high thermal efficiency of combustion. hopper are used for manual feeding of raw material during operation and additional feeding. Units used may be a screw conveyor, a pneumatic conveyor, or belt conveyor. Let's move on the next point. The biomass stove must be evaluated under standardized tests to compress the efficiency of the furnace. There are many factors that affect to quality to the biomass stove, which demonstrate the thermal efficiency. The first one is coating or insulating together with the combustion chamber reduce the heat loss rate. Moreover, there is sufficient air supply factor that can cause the biomass to complete combustion, and the emission is a quarter variable that should be considered in the efficiency of stove combustion. I would like to recap on the main point that we have covered today. Is you want to design and development biomass gasifier stove, you should study and collect more information for a high performance of biomass gasifier stove, includes theory, process, principle of the design. Finally, I hope this review article provide knowledge and information for you, and I can use this article for design my biomass stove sterilization process in the future.
Okay. Thank you for letting me join this conference. I am Gittipong Yawaja.
Okay, so is there any question to the presenter?
Can I just have one, Mohammed?
Yes. Yep.
Thanks for the presentation. I think I have a quick one, because you have different type of, of kiln or design. Have you looked at the moisture content of the material you put in, and how would that affect the efficiency of the different design? Back to you.
Author, can you please respond? The presenter.
I think he's still on mute.
Can you please
Yeah, Katsa, you are on mute. Can you just unmute your microphone?
Can you please
Yes, yes. No.
release the question again?
Oh, the question again, yeah. So you have different designs, and then you investigate different design, different material used to construct the different kiln. So what my question is, have you looked at the moisture content of the material you put in, and how would that affect the efficiency of each design?
Can you unmute, please?
Yes.
Okay, so we cannot hear anything. So
It's okay. It's okay. Back to you, Mohammed.
okay, no, thank you. I think maybe he's not getting the question properly, and also there is a problem with the microphone. So maybe we just move forward. Like our next presentation, can I request co-chair to just run these next two papers? Co-chair for the session. Can you please run the next two papers?
Sure, I can. So next one we have will be number 54. Just 1 second. I don't think I have it in my list here.
So 54 is Mr. Kui Prahaston.
I don't think I have it. I don't have.
Hello.
I think I have it in my list, Mohammed.
Yeah.
Are you listening to me?
Yep, we can.
Okay, I'm number 54.
Yep. So I think I have a brief introduction, and then you can start the video. So our next presenter is oh, you say Mr. is someone else. Is that not you? So that's Fafason, and then the presentation will be production of characterization of corn cob biochar for agricultural use. So back to you. You can start now. Thank you.
Okay, I'm start. Good morning, dear chairman and researcher in this room. My name is Papason Ratanapaibun. I come from Major University. I would like to present my work. This title is Production and Characterization of Corn Cob Biochar for Agricultural Use. My outline of presentation including introduction, material and method, result and discussion, and last one, conclusion. Northern Thailand is a major contributor of the Thai agricultural section, growing corn as one of the economic crops. There is enormous amount of agricultural waste from corn, such as corn cob, stack, and leaf after harvest.
Good morning, my name
Normally,
is
farmers adopt burning and ash method to dispose of this agricultural waste, but this is process cause local air pollution problem, PM2.5, soil deterioration, and affect human health. Therefore, it is necessary to find usage for utilization of this waste to avoid biomass burning. Production of biochar from this waste and use them for agriculture via zero pyrolysis can solve this problem. It can add value to agricultural waste, reduce carbon dioxide, and improve the soil. Biochar is a carbon-rich material from thermochemical transformation or pyrolysis of organic biomass. Normal the fixed carbon content of about 85%. The energy value of biochar was in the range of 25 to 32 megajoule per kilogram. The biochar has less porous structure with more benefit. The pyrolysis process is a process of thermodecomposition process of lignocellulose biomass. The fundamental chemical reaction is very complex and consists of several steps. The end production of biomass pyrolysis such as biochar, bio-oil, and gas. The temperature of pyrolysis used around 300 to 800 degrees Celsius under absence of the air. So in this work, focus on the biochar production from corn cob by zero pyrolysis technology. Physical chemical property released to improve of the soil.
The material of this work was used concrete from agricultural waste. It was reduced moisture content less than 12% by solar drying. After that, it was milled by machine, remain size 1 to 2 millimeter. The method used pyrolysis by adapt from herb dryer. The pyrolysis condition use temperature of 500 degrees Celsius and use time 60 minutes under nitrogen gas. After the process, the sample was called concrete biochar. The biochar was analysis of the physical, chemical, and polar structure. The result and discussion show this slide. The use of concrete biochar was allowed 24%. The moisture content volatimeter were decreased, and then the fixed carbon and ash content were increased. It led to increased calorific were increased. The high heating value of concrete biochar was higher than the raw material, with around 25 megajoule per kilogram. The slide show result ultimate analysis. The biochar has carbon content increased to 71%. The hydrogen and oxygen were low to 3 and 10% because the chemical decomposition on the oxygenous chemical group in the biomass. The characterization of biochar show this slide. The pH of biochar around 9. The electric conductivity around 1,300 microsiemens per centimeter. And last, cation exchange capacity around 100 centimole per kilogram. This slide show morphological of biochar. The concrete killing show to have no porosity, but concrete biochar was shown to have number of pores inside and increased porosity after pyrolysis. Conclusion, in this work, concrete biochar was produced from slow pyrolysis and property release improved to soil. When analyzed biochar at temperature 500 degrees Celsius at 16 minutes, it gives yield of around 34%. It gives a high heating value around 25 megajoule per kilogram. The morphological structure, the concrete biochar, high porosity and surface area were good for agricultural use. Converting corn waste into biochar was useful and had potential to be used in soil improvement. We would like to thank School of Renewable Energy Major University under the project and development of ASEAN Renewable Energy Potential Graduate Scholarship of Graduate School is Startup Project Major University, and last scholarship of the Energy Policy and Planning Office, Ministry of Energy, Thailand. Thank you for attention.
Thanks for your presentation. It's a good one. I think I will open the floor to the panel first. So I think the chair and the co-chair may have the question first, and then I'll open the floor to everyone. So Mohammed Rasul, do you have a question for the presenter?
Yeah, okay, thank you. I think it's a really appreciable that you finished within 8 minutes. So that's really good. So anyway, I think it's a very nice topic, and I also work in this area. Now, my question is, did you do any experiments for different temperature and for different timing, or for different residence times? Have you done all those experiments? So if you have done, then what is the optimum efficiency, and what is the just optimum efficiency in what temperature and what residence time, and what residence time, temperature, and there was another function I said. But anyway, so what is the optimum or maximum efficiency you get from the pyrolysis? At what temperature and at what residence time?
So the presenter, yeah.
Optimum, this work use temperature of 500 degrees Celsius at 60 minutes.
Yeah, that I have seen, but what I'm saying is, have you done more experiments like at 400, 500, 600, 700, 800? Have you done any experiments on that?
I test temperature at 300 to 700, but optimal temperature is 500 degrees Celsius because has high quality.
Okay, no,
Yeah.
thank you.
So that's
No, I
the
think
highest
you can-
efficiency already. Yeah.
Yeah, so you can
Yeah.
open the question to the floor.
Yep. Thank you. So I think I have a quick question too. In one of the slides, you said that in the chamber you also have nitrogen, which is N2. So do you have to sustain the amount of nitrogen in the chamber, or you have to supply, or is it just stay in the chamber and then you keep on using the amount of nitrogen?
Again, please.
Okay, no. I think the purpose of nitrogen is, in the beginning, you have to purge the nitrogen so that all the oxygen from inside the reactor, it goes out.
Yeah.
And then you stop the nitrogen. Just in the beginning, you purge the nitrogen so that all the oxygen goes out. You don't have to run all the time.
Yeah. So I think I'll open it to the floor. We still have another 2 minutes. So anyone else want to have a question? You can please ask. Turn your microphone on.
I have a quick one.
Please do.
Have you considered about the processing cost of turning to the biochar? Because I see that you are from the startup, something from Metro University, so you might have to consider about like the processing cost of turning this into the biochar products.
Biochar cost have cost 50 baht per kilogram.
The one that you try to convert to, right? This is from your process, right?
Yes.
Okay, it's around $0.5 per kilogram. Okay.
Yeah, that is not the production cost. This is only the cost of the char produced. So, but if you want to do say cost analysis, then there are a lot of other things you have to consider.
Yes.
So I believe she hasn't done any cost analysis.
Okay, that's only the experiment.
Yeah,
because the problem in this area is that if you need those things to convert to biochar, you have to put a lot of money on like harvesting, getting those corn cobs to do the process, and this is
you have to do construction too, and then running costs too. Yeah.
Okay.
Thanks for the question. We still have another 1 minute, so I think we can take another question. And in the meantime, can I please have the next presenter ready, please? ID 56. So I open the floor to one more question. No, it seems like there's no more questions. So can I have the next presenter ready, please? So paper ID 56. So carbonization of oil palm empty fruit bunches in a fixed bed pyrolysis reactor for community use. So the presenter is P. Com Kiao. P, are you here? Yep.
I think you should stop sharing so another one can share their screen.
I think another one can just start sharing.
Can you hear me?
He cannot share. He cannot share. Papasan, can you stop sharing your screen?
Right, the stage is yours. Take us away.
Okay. Hiện Nam quý vị. Okay. Good morning. I'm Israel Satya. I'm come from. Oh, sorry.
Start the presentation. Yeah, it's okay.
Yeah. Sorry. Good morning. I'm Israel Satya. I'm come from School of Renewable Energy, Metro University. Today I would like to present about research. The topic is analysis slow pyrolysis process of oil palm empty bunch of developed fixed bed pyrolysis reactor. My content is 1. Introduction to objective 3. Material and method. 4. Research result and discussion. 5. Conclusion. 6. Acknowledgement. Introduction. Oil palm is an important.
The presentation is not moving. The screen is not moving.
Okay.
So make sure that you share the right screen. Yep. Oh no. Share the screen again.
Okay.
Yep, that's good.
Oil palm is an important economic crop for Thailand and Southeast Asia. Thailand produces more than 4.5 million tons per year. And there is also a continued increase in the amount of palm oil. As a result, the price of oil palm decreased, which affect the oil palm farmers. Charcoal and wood vinegar is suitable for farmer due to charcoal can be used as a household or upgrade into the charcoal briquette for sale to generate income, and wood vinegar can be used as a pesticide, which can reduce to the expenditure of farmer. And past production of charcoal, the use of inefficient charcoal making furnace resulted in lower production and quality of charcoal. Therefore, this work focused on the experimental investigation on the effect of pyrolysis temperature and residence time on chemical property, yield, and calorific value of biochar obtained. Design and construction of a fixed bed pyrolysis reactor for use as a community prototype. This picture is a sample diagram demonstrating an approach to the study by testing the property of oil palm branch with an electric heater that can control the temperature, which will get the product out as charcoal, wood, vinegar. The resulting product are then tested for chemical property and calorific value in order to design a pyrolysis reactor to be suitable for the production of biochar and wood vinegar at the community level. In term material and method, the palm branch were dry and removed to reduce the moisture content to less than 20%. It was then chopped. This picture is electric heater 5 kilowatt ceramic insulating was able to heat 1 to 10 Celsius degree per minute. Above is a tube to receive nitrogen gas. The combustion process begins in the furnace. Nitrogen gas acts as a regulator that does not allow oxygen in the environment inside the furnace and does not cause fire to occur. At the bottom of the heater, there is a thermocouple used to measure the temperature of the pyrolysis process. And the lower part also has a tube for transporting the pyrolysis gas to the heat exchanger with water and ice is a heat exchanger. In order not to overheat the electric heater, circulating cold water in a heat exchanger by a water pump of 60 watt. Pyrolysis temperature and residence time were varied in the range of 300 to 600 Celsius degree and 60 to 180 minutes. Effect on approximate composition of biochar. On the picture on the left, the suitable pyrolysis temperature should be in a range of 400 to 500 Celsius degree. On the picture on the right, show the maximum fixed carbon obtained was 69.39% at 180 minutes of residence time with a moisture of 4.8%. Production yield, the optimum temperature pyrolysis was obtained at 400 Celsius degree and residence time in a range of 60 to 120 minutes. Biochar was ASEP between 28.6 to 30.5%. Wood Vanica was 17.55 to 20.53%, and the rest was pyrolysis gas. Energetic content of Bersha. The maximum was achieved at 400 Celsius degree and 120 minutes. It should be noted that Bersha with maximum HHV had a low production yield. For the design and construction of the fixed bed pyrolysis reactor, the combustion chamber size is 0.91 cubic meter and pyrolysis chamber is 1.7 cubic meter. The stack is 4 meter. Wood is used as the material for heating. Heat the system, the heat exchanger measure 1.91 cubic meter with water as the heat exchanger. Conclusion: this study showed that the OPFB, oil palm empty food bunch, was suitable to be used as a raw material for Bersha and wood Vanica production with a carbonization process, increasing pyrolysis temperature and time result in the decrease of volatile matter and moisture content will the carbon and ash content increase. Maximum productivity of Bersha and wood Vanica could be obtained at the temperature in the range 400 to 500 Celsius degree and the resident time more than 1 hour. Acknowledge. The author would like to acknowledge support for the graduate scholarship program on production and development of renewable energy in ASEAN of Metro University, Thailand Science Research and Innovation Office, the National Research Council of Thailand, and the Office of Architectural Research and Extension for Financial Support, the Energy Research Center, and School of Renewable Energy, Metro University, and thank you for providing facility and equipment. Thank you for your attention.
Thanks for your presentation. So I think I just put it to the floor first. Do you have any question?
I think
please ask. Yep. So Mohammed, you want to have a question?
I have. Maybe you can ask the audience.
Yeah,
first.
yeah. I ask the floor first. I'll come back to you. Anyone from the floor? Okay, be mindful of time. So if I have no question from the floor, I think I'll move to Mohammed. Before you ask the question, can I please get the next presenter ready? And back to you, Mohammed.
Next presentation will be on video. So I'll run the video from here.
Yep. Yes, you can ask the question.
So anyway, thank you very much for your presentation. As I said earlier, this is my area of research also, that the the pyrolysis, gasification, etc. So anyway, I think it's a good finding that you did experiment at different time and also at different temperatures, and you got the optimum around 450 to 500. That's good. And optimum residence time is about 1 hour. That's really good. But my question is, like the char or biochar you are getting, what is the difference in properties if you do experiments at 300 or if you do experiment at 600? So have you done that comparison of the properties or maybe comparison of the higher heating values?
Yeah, muted now. It's all right. I think you are muted.
Me?
No, you are okay. The presenter is muted.
Uh, 26 megajoule per kilogram.
Yeah. Okay. So let me explain it differently. Now, you have done the experiments from 300 to 600 degree centigrade. Okay. And also you have done the experiments for different time, like 1 hour, 30 minutes, 2 hours, etc. So if you do experiments for, let's say, for example, 300 degrees C and also 500 degrees C for both for 1 hour, then what is the difference between the higher heating value at 300 and at 500? So is there any big difference that heating value of char, biochar? No, that's okay. No problem. You can do it, no problem.
Yeah, I think I give it back to you then, Mohammed. You can start the next one.
Okay, so next one is I think paper 72.
Yep.
That is on temperature distribution and properties of biochar from 2 heating storage scale. And the presenter is Chayakan Sitwar. Okay, I'll just run the video. Chayakan, are you attending?
I think I can see the name there, so should be here.
So I'll just run the video first.
My name is Chiang student. I am a master degree student, Faculty of Engineering and Industry at Metro University. Today, we present temperature distribution and property of biochar from a two-heat tester, Chiang. Introduction.
Can everybody see the presentation?
Yep.
Sites above agricultural waste such as livestock, corn crop, and wood chip. Some agricultural soil are populated with heavy metal. There is a need to fight and the environmentally friendly effort for managing this agro waste and improve the soil from agricultural. Pyrolysis is one of the important thermal conversion methods in the population of biochar. Increasing the pyrolysis temperature during biochar production leads to carbon production and thermal stability. Important properties of biochar include electrical conductivity, pH, SEM, and friction strength capacity. Biochar can to improve soil fertility and reduce removal, carbon sequestration, and soil permeability solution biochar has several unique properties, making it the efficient, cost-effective, and environmentally friendly material for removing very contaminated. The objective of this work is to improve the property of biochar from agricultural waste product from single state and two-state process. Material and method. Biomass feedstock. This study used 3 types of material: corn cob, light hard, and long can piece. Each experiment used 6 kilograms of raw material at a time. Design of a biochar kiln. The biochar kiln used here was of concentric cylinder design. Its external cylinder was made of a carbon steel sheet with a unit capacity of 50 liters and a diameter of 500 mm multiplied 380 mm. The inner cylinder of the biochar kiln was selected as the center of the biochar kiln. The core was made of perforated carbon steel pipe with the inner diameter of 110 mm, a height of 610 mm, and a thickness of 2.5 mm. The electric heater of up to 15 kilowatt power was wrapped around the outer cylinder. Production of biochar feedstock with load in the annular space of the biochar kiln allowed the core. The list was primarily called for a single state process. The kiln was preheating to 300 Celsius in 1 hour. Kept starting at 3 Celsius for about 3 hours and shut down. For a two-stage process, the kiln of preheating to 300 Celsius in 1 hour, kept starting at 300 Celsius of about 3 hours, then cool down to 100 Celsius in 1 hour, and heated to 300 Celsius in 1 hour and keep at this temperature of about 1.5 hours and shut down. Working shift of biochar. Working shift of biochar incinerator a photo of biochar after incineration. Result and discussion. Temperature distribution inside the biochar kiln. It could be seen that our biochar kiln could control the temperature better. The peak of the temperature when no swing rank was stable at the traditional kiln. The traditional kiln show at higher temperature. Different that occur temperature distribution in statement and state 2 as lost as in the additional furnace.
think someone is sharing the wrong screen.
Product. The Concord biochar yield from the two-stage mode was 36.7%, higher than the single-stage mode of 33.3%. In contrast, light hot and long-term peak biochar yield increased from 45% to 43.3% and 43.3% to 38.3% from the single state to two-state mode, and an additional include in heating time from the two-state mode appear to decrease the biochar yield. However, the result also depended on the density of agricultural resources, pH and EC. The pH analysis result of the biochar. The Concord biochar pH value decreased from 8.08 on the single state to 7.3 on the two-state king. On the contrary, the pH volume of the light hot and the long-term peak biochar were increased 6.96 to 7.34 and 8.76 to 8.96 respectively. The pH was between 7.07 to 8.79, which were celebrate property of axis soil improvement. The electrical conductivity analysis result of biochar from the test is what found that electrical conductivity from Concord, the light hot and the long-term peak biochar improves as shown in the picture. Same. In the two-state mode, produce biochar with higher porosity than the single-state mode of all feedstock, consequent as the pound area of the biochar increased. It became more celebrate of soil improvement. The biochar pound area would help absorb water or other nutrients in soil. Conclusion 1. The developed king had better temperature control than the traditional king. 2. The longer heating mode appeared to increase Concord biochar yield, but reduce the biochar yield of light hot and long-term peak. 3. Biochar properties such as the electrical conductivity and porosity of biochar from Concord, light hot and long-term peak were improved are better than traditional kiln. Literature. This was referenced in the light of this paper.
Okay. I think
Thank you for listening to the presentation.
Okay, no, thank you. Strong to you.
I don't have any question. I think we can just leave it to the floor. What do you think, Mohammed?
Okay, yeah. Any question from the audience? Okay, so looks like there is no question. So maybe I'll just ask one question. I observed that your two-stage heating is better than one-stage heating. Do you know what is the reason for that? May I know actually what could be the reason for having say better results in two-stage heating compared to one-stage heating?
I don't understand your question. Again, please.
Okay. So two-stage heating has better performance compared to one-stage heating. So what is the reason? Why? Okay. I think no, that's fine. Don't worry about that. So anyway, I think you presented a lot of information that is really good. And there are a lot of other things to be done, particularly if you take say biochar, then you convert it to a carbon black or maybe activated carbon, or you can use that one as ammonia fertilizer, etc. So you can do some more research on that. And similarly, that the gas you are getting, you can convert that into hydrogen. That is also possible. And the oil actually you are getting, you can convert that through distillation and then hydro treatment, and then you'll get very similar to what is the standard diesel. So there are a lot of aspects you can work on that area. So anyway, thank you for your presentation, and it's a good content. I like that, and hopefully.
And I think the presenter can also think of gasification, with higher temperature too. That's another approach.
Yeah, that's true. That's true. So there are a lot of avenues to work on that one. So yeah, please try to explore those avenues. So I think we have finished in this session, and all the presenter, and thank you very much. And if there is any good luck for your best presentation, then we'll hear from the committee. Okay, thank you very much. And your next session will start maybe after 15 minutes.
Thank you.
All right. Thank you.
Okay,
Thank you,
then we'll
Professor.
just log out now.
Professor Rasool and Trun, thank you.
No problem.
And also
My
thank you
pleasure.
all of you, and we'll just in 15 minutes we'll start our next what's called session. Yeah, so just take a break and make yourself comfortable.
Okay.
Thank you.
No problem.
Thank you, Harun.
Thank you.